Hi, I'm Mark Ferbiak, and it is my pleasure to offer you an overview of our article titled Hybrid Obfuscation to Protect Against Disclosure Attacks on Embedded Microprocessors. This is joint work with my colleagues Simon Rokicki, Nikolai Bezants, Russell Tessier, and Christoph Paar. Embedded microprocessors with limited resources are vital in a wide range of low-end computing platforms, such as the Internet of Things or infrastructure monitors and sensors. However, these processors must operate in severely constrained environments where attackers may have physical access to the device. Hence, attackers may analyze the device to eventually reverse engineer the firmware. A fundamental problem is that the reverse engineer typically knows the instruction set architecture encoding and is thus able to transform the firmware image into a human-readable representation. Our main question was whether we can leverage a combined hardware and software obfuscation approach to prevent a physically present attacker from determining the ISA encoding of a simple low-end microprocessor. Before we turn to our hybrid obfuscation scheme, we first define our trust assumptions about the system and the adversarial capabilities. In our system, we assume a simple RISC-based processor architecture without any caches. External program memory and its buses are not trusted, since an adversary with physical access can eventually tamper the memory and the buses. Furthermore, we exclude any advanced invasive hardware attacks such as microprobing. We also exclude the use of any debugging capabilities a device might have. Instruction execution results in a variety of actions such as updates of the register file or the status flags. Even without detailed information of which instruction has been executed exactly, the attacker is able to gain information about the ISA encoding. For example, the adversary obtains the address of the next fetch instruction by observing the program memory bus, as pictured in the graph on the right. As you can see, all control flow instructions as well as the dynamic control flow graph are immediately revealed by looking at the dotted lines. In case of an unknown instruction encoding, the control flow instructions can be used to derive partial information, since the attacker can tamper the instruction and observe changes in the next fetched instruction. We can then leverage this information to derive the encoding, especially for ISA randomization schemes that are based on XORing or instruction permutation. Besides control flow related instructions, other possibilities for determining the ISA encoding include exploiting I/O instructions or measuring execution times of instructions. Please have a look at our paper for further details on these possibilities. We now sketch the different hardware-level obfuscation techniques that we implemented for a simple RISC processor. Note that we, at this stage, are using obfuscated instructions. As such, the first step is to substitute the opcodes with their original representation. The second step is to permute the operands to their original values as well. The third step involves mitigating attacks based on I/O instructions. To this end, we limit access to general-purpose RAM and register files to the I/O instructions. We enforce this limitation using a memory address sanitizer. The fourth step adds support for retrieving evidence of tampering for any invalid memory accesses or malformed operations. Since a general limitation of hardware-level obfuscation is the preservation of the program structure, we additionally add software obfuscation techniques such as control flow graph flattening or splitting of large basic blocks into approximately equally sized chunks. To further remove program characteristics, instruction substitution is used to replace instruction sequences by other functionally equivalent but more complex instructions. For our hardware implementation, we employed the SPREE soft processor generation framework and extended it with a custom RTL generator for the randomized ISA encoding, as well as our modules such as the memory address sanitizer. For the software obfuscation, we extended Obfuscator LLVM with basic block normalization and added support in the GNU assembler to apply the randomized ISA encoding. A key characteristic of obfuscation is to virtually destroy any correlation or similarity between original and obfuscated programs. To examine the program similarity created by obfuscation, we proceed in the following way. First, we select a set of programs and obfuscate them. Then, we apply a set of similarity measures to analyze the similarity between obfuscated and unobfuscated programs. As explained before, the adversary has access to the dynamic control flow graph and thus can apply graph similarity analyses to the original programs. In the left figure, we see that without obfuscation, the original program can be determined since the control flow is not altered. After applying obfuscation, we see that we can no longer distinguish the original program from the others, except for this. Since the adversary can read the program memory, he is able to apply statistical analyses to instructions. For the entropy and standard deviation of instructions, we see that the clusters are much larger and overlapping after applying hybrid obfuscation, as pictured on the right. This means that programs are more similar and harder to tell apart. In conclusion, we demonstrated that ISA randomization instantiated with hybrid obfuscation can protect against attackers with limited physical access. Moreover, we provided a novel assessment strategy to analyze hybrid obfuscation schemes. Thank you all for your attention, and please have a look at our paper for further details.